Welcome to Let's Get to the Marks, going through the AQA GCSE Combined Science Trilogy, Chemistry Higher Paper 2019. There are 6 questions. Let's get into it. Okay, excuse me while I have a sip. This question's about the reactions of metals. Figure 1 shows what happens when calcium, copper, magnesium, and zinc are added to hydrochloric acids. What is the order of decreasing reactivity of these 4 metals? So you can see we've got 4 metals in test tubes. They've been mixed with hydrochloric acid and we got bubbles, and it tells us these bubbles are made of hydrogen gas. They're coming off. So it asks us for the decreasing reactivity. That means we want to start with the most reactive and work down to the least reactive. What's the correct order? Let's zoom out so we can see this. Okay, so it looks like calcium is the most reactive. How do I know? It's releasing more bubbles of hydrogen gas. So I'm going to cross this one out and that one out because we want to start with calcium. What's the next most bubbles? Magnesium. So it's going to be this one, calcium, magnesium, zinc, and last of all, copper. So that is the order of decreasing reactivity. Hokey dokey, let's move on. What I suggest you do is grab a paper, grab a pencil, uh, press pause at the start of like this slide and basically, or this sheet of paper that you can see on the screen right now, whatever I'm waffling about, hit the pause button, have a go at the questions. Unpause, check your answers off against mine. All right, let's go. A student wants to make a fair comparison of the reactivity of metals with hydrochloric acid. Name 2 variables that must be kept constant. So they're looking at these 4 different metals. What if you're looking at how 4 different types of metal react? What should they have kept the same about this? And of course, the hydrochloric acid. There are 2 things you can keep the same, and that's the volume, which means the amount. When you're dealing with liquids, we call it a volume. But you also need to keep the same the concentration, which is how many hydrochloric acid particles are in that volume. So there are 2 factors we could keep the same. Another thing that would affect how quickly they react is temperature. So you might want to put these all in a water bath, keep them at the same temperature. And the other thing is surface area. Notice they've used a lump of each of the metals. You wouldn't want to chuck powdered calcium in or powdered copper because that would have a larger surface area and may react quicker and wouldn't make for a good comparison. So I'm going to go for 2 of those. I'm just going to say volume of HCl and concentration of HCl, but I would also say temperature, which you could use a water bath, surface area by keeping them, which they think they've already done. They've kind of used lumps or they haven't used powder and lumps. Right. What is the independent variable? What were they changing in that picture? What was different about the 4 test tubes? It was the type of metal. Independent variable is always what you're going to change. So that should go bish, bash, bosh. 3 marks. Predict the reactivity of beryllium compared with magnesium. Give a reason for your answer. Use a periodic table. So if we checked out the periodic table, I'm going to save you the hassle, but you can pause the video, have a go now. If you check out the periodic table, um, beryllium's here, and beryllium has 2 shells, like that. And it's got 4 electrons. Check it out, check it out. What does beryllium want to do? It wants to give these electrons away. What's stopping beryllium from giving the electrons away? Well, what's stopping it is that beryllium has it's 4 protons. So it has a 4 plus charge in the nucleus, and that is pulling in that negative electron. It's actually trying to attract it and pull it back to the nucleus. If we look at magnesium, magnesium has a plus 12 charge. They did say magnesium, didn't they? Yeah, beryllium compared with magnesium. Just checking. But the difference with magnesium is magnesium um, is a period down. So magnesium has an extra shell of electrons. Look at this crusty D grade GCSE art drawing. That's a level 3 or 4. That's no good, is it? Okay, so what's the difference? Well, look, although it's a bigger positive charge, you might say, oh, look, it's a plus 12 charge. Yeah, but look how far away the charge is. And so if we increase the distance, it's easier to give this electron away because it's further from the nucleus. Not only is it further, but it has this extra shield of 8 electrons, and we call this shielding. So as you go down the group of any of the metal groups, so group 1, group 2, and group 3, as you go down the group, they become more reactive as you go down the group. And it's because it's easier for them to lose electrons, which is what metals try to do. And metals always try to get oxidized. They try to lose electrons to become positive, and so that they can get a full outer shell. And it's always easier as you go down the group because the atoms get bigger, they have more shells, some more shielding, and the electrons are further from the positive charge of the nucleus, so they feel the force of attraction less. Oh my good gosh, only 2 marks, and I waffled about 22 marker there. So I would say beryllium is less reactive. We could argue, we could either say, I've just argued saying magnesium is more reactive, so it doesn't matter which way you go. I've just gone for the beryllium less reactive. And this is a slightly different explanation. I'm just going to say it's smaller, okay, and probably on the same marking point, you could say it has less shells, outer electrons closer to nucleus. Okay, so the outer electrons are closer to the nucleus because it's smaller, so that's kind of like 2 points. And then what I want to hammer with is so feels stronger force of attraction to nucleus. Notice the way I put feels a stronger force of attraction. It doesn't necessarily mean there is a stronger force because, of course, its nucleus has less charge than this one, but this one feels more strongly attractive because it's closer. Okay, and also this is more of an A-level thing, but I could say it has less shielding. Now, if I was trying to argue the reverse of this, which would also get you 2 marks, I could have said magnesium is more reactive, which is answering the same question. And then I would have just said the opposite because it is bigger, it has more shells, electrons are further from the nucleus, so they feel less attracted to the nucleus or a weaker force of attraction, and there's more shielding. Bloody blah. I'm going on. Let's move on. Right, 1.5, a solution of hydrochloric. Wee, I need to zoom in. A solution of hydrochloric acid contains 3.2 grams of hydrogen chloride in 50 centimeter cubed. Calculate the concentration of hydrogen chloride in grams per decimeter. Listen, people, the amount of students I teach that do not get this and they lose these 3 marks. Now, you are going to be getting your grade awarded on a grade boundary. That means you're competing against everyone else in the country. So you can pat yourself on the back when you get an easy question right. But if you get a question right that everyone else in the country is getting right, you're not separating yourself, moving up through the levels. So you need to get these kind of questions right because you know a lot of people are dropping marks on this. Don't be one of the people dropping the marks. Learn this equation off by heart, and it works every time. First thing to do when you're confronted with a maths question, because it has numbers in the sentence, circle those numbers and identify what they mean. 3.2 G. Are we talking about like 3.2 thousand pounds in the back pocket? No, we're not talking about 3.2 G. We're talking about 3.2 grams. And what is that? That is mass. Okay, so label it as you go through your exam. That is mass, capital M. What is this? 50 centimeter with a little 3. That's cube. That's volume. So you need to label this. Now, when you write M and V, this will trigger your brain. You don't need to know the rest of the question. I don't need to read anything else. M and V tells me I need to use this equation. If you haven't learned this equation off by heart, what are you doing? You're going to lose 2 or 3 marks in your exam because they're going to ask you one of these questions in your GCSE exam. And if you don't know this equation off by heart, you're going to lose the marks. It's mass over concentration times volume. So I've located that I have M and V. That means I'm definitely looking to calculate the concentration. Okay. And all you have to do is M divided by V equals C. So M over V equals C. Now, if you just do 3.2 divided by 50, you are going to get 2 marks. But you're not going to get all 3. Why? Because volume, so this is a little bit harder. In chemistry, we are supposed to convert centimeter cubed into decimeter cubed. Volume is always in dm, and you do that by dividing by 1,000. So actually, if you do 3.2 grams over 50 centimeter cubed, you're only going to get 2 of these 3 marks. So your best bet is to do 3.2 divided by brackets 50 divided by 1,000. And that is the same as saying 3.2 over 0.05. And if we do that, Bob's your uncle, Fanny's your aunt, 3.2 divided by 0.05, that is 64. And the answer for three fat marks, boom, is 64 grams per decimeter. So, guys, there is no excuse for you not to get these right. Approach every past paper like this, circle the numbers, identify them, recall that equation. You're not going to get an equation sheet in chemistry before you ask. Yes, you might do in physics. You ain't getting this in chemistry. Learn it. Come up with something. Mum, I don't know, something rude. Mum, Chris, Victoria, whatever, Mark sits on, I don't know, someone, Charles is something beginning with V, whatever. Come up with something stupid, come up with something ridiculous in your head that makes you smile, makes you laugh, makes you remember M over CV. All right, let's move on. Right, two. This question's about salts. Ammonium nitrate solution is produced when ammonium gas reacts with nitric acid. Give the state symbol for ammonium nitrate solution. So they've just told us ammonium nitrate is a solution. What's the state symbol for a solution? Hopefully you know this. It's AQ, stands for aqua or aqueous, which means water, okay, dissolved in water. So that is the state symbol. Then it says, what is the formula of nitric acid? So let's just zing a tick there, and I need to clear this and move down because I haven't got all of this question here. So what is the formula of nitric acid? Is it HCl, HNO3, H2SO4, NH4OH? Well, hopefully you know that HCl is going to be hydro um, caloric acid. It'll only be hydrochloric acid if it's in aqueous, but that's another set thing. This is sulfuric acid. Hopefully you can see that from the sulfur atom. They're the two main ones you'll be confronted with in chemistry. And this is something called NH4 is known as ammonium, not ammonia, ammonium, and that is ammonium hydroxide. And this is nitric acid, HNO3. And you only need to know these three formulas: hydrochloric acid, nitric acid, sulfuric acid. You need to know those off by heart, guys. So learn them, put them on a revision card. What are the names of the three main acids in chemistry? And it's hydrochloric acid, nitric acid, sulfuric acid, and the formula. So on the front of your revision card, if you've got a question card, write down what's the name of the three main acids and what is their formula. And then on the back, put hydrochloric acid HCl, nitric acid NHNO3, and sulfuric acid H2SO4. You should learn them off by heart. If you don't know them now, you better learn them. Right, let's go. 2.3. I've had a lot of coffee today, so I'm a little bit hyped. 2.3. Ammonia gas dissolves in water to produce ammonia solution. Ammonia solution contains hydroxide ions. A student uses universal indicator solution to, oh my days. A student adds universal indicator to solutions of nitric acid and ammonia. What's observed in each solution? So universal indicator, guys, that is that you'll recognize this from class. You have a little kind of dropper lid like that. Yeah, check out the drawing. They robbed me. They robbed me when I did my GCSEs. They stole my. I deserved an A in art, but they stole my grade. Gave me a D, a level 3. They ruined me. All because my sketch pad wasn't good. Right, universal indicator solution. That's that dark green solution. You take a drop out, you drop that, and it changes color, and then you match it up with a pH scale. So what color would you get with acids? So nitric acid is a strong acid. You're going to get red, but I guess they might give you the mark for orange or yellow because they're also colors of acids. And ammonia solution is an alkali. So I'm going to go blue. The strongest alkali give off purple, but blue is a safe bet because alkalis are like the colors of the sea, and acids are the colors of fire, red, orange, and yellow. Alkalis you can think of the colors of the sea. They're like blue and purple, kind of go bluey green to blue to purple. Okay, let's zing on. Ba-ba-da-ba. The student gradually added nitric acid to ammonia solution. Which row, A, B, C, or D, shows the change in pH as the nitric acid is added until it's in excess? So we know the nitric acid is added until excess. So what would the final pH be? If you keep adding acid till there's nothing else left but nitric acid, what would the pH be? Well, the pH is the student gradually added nitric acid to ammonia solution. Shows the pH as the nitric acid is added until excess. pH of ammonia at the start is going to be like pH 10. So that's be one of these. And then I'm guessing D is, look, so the acid has to be one or two. That has to be the right answer. But ammonia is not neutral. Ammonia is an alkali. So ammonia acts as a base. So we're going to go like that. And that's the correct answer. But I understand if you went for the that one because nitric acid is a strong acid, but it didn't start off at the right pH. If it was water, it'd be pH 7. All right, let's move down. That was D, that answer. Right, 2.5. Calculate the percentage by mass of oxygen in ammonium nitrate. Relative atomic masses, H equals 1, N equals 14, O equals 16. Relative formula mass, NH4NO3 equals 80. They're basically saying, as a percentage, how much nitrogen, no, sorry, how much oxygen is in NH4NO3. So what you want to do is there are three oxygens in there. So you want to do O3 divided by the total. And that's NH4, loving a pink color. NO3 like that. So you want to do that over that times 100 to get the percentage. And it's a lovely three fat marks. Let's go and do that. So I want 3 times 16, that's 48. And then I want to divide that by 14 plus 4 because nitrogen's 14. Each hydrogen is worth 1. So plus 4 plus 14 again. Oops, little plus sign, please. Plus 48 for the 3 times 16. And then I just need to add that all up. Let's see if I can do it in my head. 14 and 14 is 28. Plus 4 is 32. Plus 48 is 80. Why am I adding it up? Oh my gosh, have you ever seen someone so thick? Oh, Sugar Ray Leonard. There's 80 there. They've given us the blooming thing to save us adding it up. So it's 48 over 80 times 100. And that's for all the marks. 60% of ammonium nitrate is oxygen, and that's going to get you 3 fat marks. So you're going to get a mark for working out that that was 40. You're not going to get a mark for working out the 80 because they gave it to you. So even if if you're stupid like me and you added it up because you didn't pay attention, 48 over 80 times 100, and you get 60%. Beautiful. Let's move on. Hokey cokily 2.6. Describe a method to investigate how the temperature changes when different masses of ammonium nitrate are dissolved in water. You do not need to write about safety. It's 6 fat marks. So what do we want to do? They're telling us what the independent variable is. Different masses of ammonium nitrate are dissolved in water. So I'm going to use 5 different masses. I want to say what my independent variable is. So for my IV, use 5 different masses of ammonium nitrate. Now, don't be afraid to actually give the examiner some masses. So I'm going to do that. I'm going to say 1 gram. Now, you just think, don't go like 50 grams or something crazy like that. When you're talking with powders or solids, just use a couple of grams. So 1 gram, 2G, 3G, 4G, 5G, and you can weigh them on a balance, obviously, to get that. So use 5 different masses of ammonium nitrate weighed on a balance. Make sure to zero the balance each time. So what we're saying there is make sure that you zero it so you don't get zero error. So weigh out 5 different masses, going to get a mark for that. Now we want to find how their temperature changes when they are dissolved in water. So here's the thing. We're going to put them, you might say put them in a test tube, but it's more accurate. Oh my days, let's get rid of the pink there. It's not time for pink. Right. We're going to use a polystyrene cup. But what I can do is get a beaker. This is a bit extra, okay? You don't need to do all of this, but this is just if you really want like the fancy pantsy version. Take a polystyrene cup rather than a glass beaker. Let's slam a lid on that polystyrene cup and let's bash a thermometer through there as well. Right? I want to pour my water in there and take the initial temperature. So what we're going to do is say, measure out 50 centimeter cube. Why 50? You could say 20, just a sensible amount. Measure out 50 centimeter cubed of water. uh, with measuring cylinder. Now, this might be a bit extreme, but I'm going to say measure at eye level. Okay, I'm going a bit extra above and beyond, but on a flat surface. So this is all good practice. You probably don't need to put all of that, but you know, why not? Why not put extra stuff in? So, and then what do we want to do? Pour water into a polystyrene cup. Okay, I'm going to use a polystyrene cup. You'll notice I drew a glass beaker around the outside with cotton wool for extra insulation, but I might not even bother waffling about that because you're not going to need all of that as long as you've mentioned some insulation. And there's a reason why, because we're going to be measuring the temperature. We don't want the heat to be escaping. Some is going to escape, but if we can minimize that, our results are going to be a lot more accurate. Okay, and so what I want to do now is say, um, measure the starting temperature of the water using a oh my days, thermometer. Now, I'm probably going to run out of room, but what you should do is record the starting temperature of the water. And I would give it a minute before you do that, just to give time for your temperature to get the proper reading of what the water is, because it's been reading the air when it's been sitting outside. It takes a little time for it to get for the colored liquid, the red liquid inside, to move up to the right temperature. So give it the time so that it rests at the right temperature. Anywho, we could put that in, but let's not get too extreme. Right, we've measured the starting temperature. Now what I want to say is add the first mass of ammonium nitrate. Stir once. We don't want to, we're just going to give it one stir. Keep that the same each time. Uh, um, yeah, and what do we want to do? Put a lid on and record the temperature every, what do we want to say here? Let's say every 30 seconds. So what you're going to do, you're going to record the temperature every 30 seconds. Bish, bash. Now, when we finish, um, yeah, what do we want to do next? Okay, record the biggest difference in temperature. So, and then you can repeat for each mass. And then I didn't say for 5 minutes. Let's do that for 5 minutes. And then what we can do is record the biggest difference in temperature and then repeat for each of the masses. Yeah. I could say repeat 3 times, take an average, or I could say repeat for each of the masses above. I think that's it. I think that's it, man. Right now, if we were going on some next extra thing and you wanted to find out what the highest temperature change is, you can actually plot a graph to do that. Gets a bit rough though, people. And I'm not sure at GCSE you would need to do that. So what you would do if you wanted to find out what the highest temperature is, you have temperature on the side here of a graph, that's temperature. And down here is time, gets a bit confusing, 2T's. So this is temperature in degrees. And what we do is we've got our starting temperature. Let's say we took 2 recordings of our starting temperature. We're like, yeah, ready to go. Let's add the ammonium nitrate. So we bash the ammonium nitrate in every 30 seconds. We are taking the temperature. What we'll probably find is the temperature might go up, then down, whatever. What you actually can do is an extrapolation graph. And what you do here is you draw extrapolation lines like this. I know, a bit crazy, right? And where the two lines intersect like this, you plot a straight line back from your trend of all your temperature change points, and where the lines intersect, that is the temperature of the initial temperature of the solution at the point of addition. So yeah, that is something else you can do, but that's a bit long to go into all that, so I'm going to skip all of that. Okay, folks, let's move on. Let's move on. Get me waffling about stuff we don't need to talk about. Okay, question 3. This question's about whoop, This question's about oxygen. Hydrogen reacts with oxygen 2H2, G, plus O2, G, goes to 2H2O, G. Figure 2 shows the relative energies of the reactants and the products at a certain temperature. Here's figure 2. Ooh, fancy. You don't normally get numbers on these ones. Okay, so we've got kilojoules of energy, 500,000, 1,500, 2,000, 2,500. We've got hydrogen plus oxygen. We've got a bit of a camel's hump. And then we've got 2H2O going on there. I'm going to minimize this a bit. Label the activation energy for 1 mark on figure 2. So the activation energy, people, you might want to pause the video, see if you can picture in your head where you would label the activation energy. We draw a dotted line across here from the products. This is reactants. This is products. And the activation energy is always energy going in. So it's energy you're putting in. So you draw an arrow going up like that. That is the activation energy. And I like to label it AE, shorthand, capital A, little e, activation energy. Okie dokie, let's move down. That would get you to Mark. Determine the overall energy change for the reaction between hydrogen and oxygen, shown in the question 3.1. Use the figure. So this is unusual. They don't often ask this, but guess what? It's actually not that hard. What we're going to do is, here's the activation energy. And what you're more commonly asked to do, which I'll do first before we get on with the question, you're asked to label the overall energy change. The overall energy change is always the difference, whether it's exothermic like this graph or whether it's an endothermic graph. It's always the difference between the reactant line and the product line. So it's the difference in this here. Now, the arrow goes down because the energy goes down between the reactants and products. It's not going up. So we draw a downwards arrow. That is a negative arrow. So we're going to use a negative number. And all we've got to do is go across here and read what that number is. And then, can I make a straight line? Probably not. I need to, you get your ruler out and you bust out a straight line there. And then it is that. So what is this? This is going up in 100s, 100, 200, 300. So that is 300. And then we've got 400, 500, 600, 700, 800. So we have 800 minus 300. So 800 minus 300. We have an answer of 500, and that's a lovely answer, but you could put minus 500. They might say ignore that, depends on the question. So overall, there is a minus 500 change in the energy. Look, it went from 800 to 300. That's minus. So it's gone down by 500, and that means it's exothermic, and that will get you all of the 2 marks. Okay, let's move on. One for the negative sign, one for the 500. Let's go. Oxygen is in group 6 of the periodic table. Figure 3 shows the outer energy levels in 1 molecule of oxygen. Draw the electrons in the outer energy levels only. Okay, we know oxygen is in group 6. They told us there. What does that mean? How many electrons are in its outer shell? You got it. It's 6. So you want to pair them up like this. It's good practice. Makes it easy. I can tell I've done 4. Now, a mistake you might make, you might go like that. This would be probably the most common mistake I'll start with. Obviously, this one has got 6. So, and you might do that and go, right, that looks great. But if we ignore all of that, we go, there's 1, 2, 3, 4, 5, 6, 7. Oh, there's only 7 electrons in here. That is not happy. And if we do the same here and look at this one, 1, 2, 3, 4, 5, 6, 7, oh, they're not happy. Now, we're not ionic. We can't steal electrons from anywhere. But what we can do is increase the amount we're sharing by doing this, putting another X, oopsie, and another O there. And now, if we look at them individually, 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. Now, if we then look at this one individually, 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. Remember, they want 8 in their outer shells. This is actually a double bond, and this will get you 2 marks. And if you represent this with the old simple model like that, that is why we show oxygen with 2 black lines. Each black line here is an X and an O, is a pair of shared electrons. Okay, cool. Anyway, enough of my whiffle waffle. Question 3 continues on the next page. Well, let's continue then. 3.4, the equation shows the decomposition of hydrogen peroxide. Okay. Right. Calculate the overall energy change for the reaction, 3 marks. So what you want to do here with these questions, and they can come. This is a nice simple one, but they can become a lot more difficult than this. Essentially, you want to write reactants. Where you see the arrow, put a minus sign, a little takeaway sign, and then on the other side you write products and then equals the energy change. You might want to check out some of my other videos. I've done tons of the C1 papers for both chemistry GCSE and combined science GCSE, because there are versions of this that are a lot more difficult, where they ask you to find the bond energy for a bond rather than the overall energy. The overall energy is just add up the reactants, 1 mark, add up the products, 2 marks, take the reactant number and take away from it the product number, and you get the final answer, 3 marks. So we'll go through that now, but they can make it more difficult, where they give you the final answer, the energy change, and they give you most of the reactants or most of the products except for one bond, and you have to work that bond out. Okay, anyway, you can see them on the other videos, because a lot of most of the exams have one of these questions on. It's either the easy version like this or a hard version. Okay, first of all, bum bum, I want to do HO, OO, and another OH. So I've got two OHs. So 2 times 463. And there's an OO in the middle there. Can you spot that? There's an OO there as well. So I want to do 1 times 138. Now, here's the thing. Notice there's a big 2. So once I've written all the bonds out, I want to put them in the brackets, and I want to do that. 2 times all of that. Let's smash that into the old calculator, see what we get. 2 times 463 plus, oh, I swear I'm mashing that up. Okay, let's just do that. And then I want to add 138. So, and then add 138. Yeah. God, I long that out. That comes to 2128. Now I'm going to put my minus sign, minus sun, all my days, 2128. And now I need this number. You will have scored a mark if the examiner sees 2128 anywhere on your paper. Now I need to do 2 times HOH and then plus 100 with a double bond. So I need 2 OHs. So that's 463 times 2, because there are 2 of them there. Look, there's 2, 1, 2. But I've also got the big fat 2. So I need to put that in brackets and go 2 times that. And I need to work that out. And then I need to plus 496, which is for the oxygen there. So let's smash that in the calc and see what we get. So we go 2 times, oh my gosh, 463 times 2, close brackets, got to use brackets a lot here. That basically is 1852. Now, if you write some of these random answers, numbers down, and you screw up overall, the examiner may give you a mark, because by seeing some of the working, they see what you've attempted to do. Oh my days, what happened there? Right, that's 2348. And all I need to do is go 2128 minus 2348. Don't worry about it being negative. That's totally cool. In fact, 90% of the reactions on Earth are negative reactions. So the answer is minus 220. And essentially what you're getting the marks for here, folks, you're getting 1 mark for 2128, 1 mark for 2348, 1 mark for doing the sum and getting the answer. 3 marks. Beautiful. Question 4. This question is about elements in the periodic table. What order did scientists use to arrange elements in early periodic tables? They they arranged them by atomic weight. Okay, so they used sort of like atomic weight. Oh my days. That's not how we do it nowadays. We don't arrange them by atomic weight. In early periodic tables, some elements were placed in the wrong groups. Mendeleev overcame this in the periodic table. What's one way you did this? So they're only going to give you a mark for the first thing you write here, because it says one way. So write your best answer first if you're going to put more than one answer, because they'll only check your first point. So give one way Mendeleev did this. I'm going to give you more than one. So the elements were placed in the wrong groups. Mendeleev overcame this in his periodic tables. He arranged by chemical properties. Da, da, da. But also, these are the 2 things, if you have to know anything about Mendeleev, he left gaps. So there are 2 possible answers that would get you the mark. He left gaps but he rearranged things by the chemical properties. He said, "Oh my gosh, that bubbles in water. Why am I going to have that in? I'm going to put all the things that bubble in water in one group over here." And then so he arranged them by their chemical properties. And where he said, "But if I do that, it creates a gap over here." He said, "Well, I'm going to leave that gap. I'm not going to try and fill it. I'm just going to leave a gap there." And so they're the two funky things he did. He still tried to arrange by weight like everybody else. That was his starting premise. But then he said, "I'm going to arrange by weight firsthand, and then I'm going to change it based on chemical properties." So he still started by doing that. Of course, we don't do that now. In the periodic table nowadays, we arrange by increasing atomic number from left to right across the periodic table. They are not arranged by mass anymore. Right, table two shows the boiling points of fluorine, chlorine, and bromine. So fluorine boils at minus 186, so it boils anywhere on the earth. There's nowhere that cold. Chlorine is minus 34. So there are places on the earth you could go to where chlorine would not be a gas. Boiling point is essentially saying gas point. Bromine, it boils at plus 59. So really we're saying this is the gas point. Explain why the boiling points are low. So yeah, if you have a low melting point, boiling point in chemistry, you are always one of these. They are simple molecules. You could say simple covalent molecules. They're anytime you are asked in the periodic table, why is this substance soft? Unless it's a metal and alloys, and that's something different. But why has this substance got a low melting point, or why has it got a low boiling point? The chances are it's a simple molecule or simple covalent molecule. It has weak intermolecular forces between the you can just say weak intermolecular forces. We don't need to say between, because intermolecular means in between the molecules. So you either say weak forces between molecules, or you say weak intermolecular forces, and that term intermolecular is saying between the molecules. So there's weak intermolecular forces which do not need a lot of energy to break. So that is the reason why water is a liquid at room temperature. That is the reason why oxygen's a gas. It's the reason why fluorine's a gas. It's the reason why chlorine's a gas at room temperature, because they've all got weak forces between their molecules, which are easy to break. Boom! I really need to cut down the espressos in the morning. Explain the trend in boiling points in table two. So this basically saying what's happening to the boiling points. This can really confuse people. It kind of mashes up your mind, because actually think of a ladder where at the bottom of the ladder it's like minus 1,000 and at the top of the ladder is plus 1,000. So we're actually climbing up the ladder, going from minus 186 to minus 34. Minus 34 is a higher number than minus 186 because it's closer to zero. And plus 59 is the highest number of all. So actually, as we go down the group of the halogens, their boiling points increase. Now, why is that? Well, the reason is because they get bigger. Okay, so here's my fluorine, and then here's my chlorine. And why does that matter? Well, when they get bigger, it means the forces between the molecules get stronger the bigger you get. So when we're trying to boil fluorine, which isn't very hard because it's already boiled at minus 186, pretty much nearly everywhere in the universe it would be a gas. And the reason is you only need a little energy to break those forces between the molecules. But chlorine is bigger and so has more forces or stronger forces between the molecules. Remember, when we're talking about simple covalent, we are not trying to break this black bond here. We are breaking forces, not bonds. So what I want to say for this answer, as I scroll down, explain the trend in the boiling points, is like this. As we go down the table, the boiling points increase. A lot of people won't have spotted that, but they increase, and that's going to give us a mark. Bish. Why do the boiling points increase? Because the molecules get bigger. Okay, the halogens get bigger, the group 7 elements get bigger, and that's going to get me another mark. So the intermolecular, you can just say forces between the molecules, but intermolecular forces are stronger. If I want, I can say need more energy to break. We already established they have intermolecular forces, and therefore the reason why you must have a higher boiling point is because you have more of those forces, which makes it you need more energy to break them. So there we go. There's our answer. Moving on. 4.5. Explain why neon is unreacted. Give the electronic structure of neon in your answer. Oh my days. So I think a neon has 10 electrons, if I remember rightly. What is neon's atomic number? Is it 10? Oh days. I'm gonna have to look at a periodic table. That is disgusting. Let's have a go. Give me 1 second, people. I gotta find a periodic table. No, AQA one. Just stay with the A, stay with the A, stay with the AQA. All right, let's zoom in. Where is old Neon? Neon's over here, so I'm zooming past Neon. That's the problem. Oh, where are you, Neon? Yeah, Neon is here. You can see it has 20 and 10. Let me zing back. Electronic structure of Neon, it's got 10, so its electronic structure is 2,8. What we want to say is Neon has a full outer shell. Okay. Um, yeah. Um, so does not need to lose or gain electrons or share. Doesn't need to do any of that stuff. So there's no need for it to react. How many atoms in 1 gram of argon? Okay, so argon has an AR of 40 and we have G. So what did I say about maths questions? Circle, circle. That is mass. And we've been given AR, baby. Now, when you're given AR or MR and you've been given mass, you're not thinking M over CV, which we did right at the start of this paper. You should be thinking about M. Some people say mass equals Mr. Moles. Or something like that. They have a funky way of remembering it. This is the most common and important equation to know in chemistry. So mass, which will normally be in grams, over the MR times the number of moles. I put N for that. So the first thing we can do here, even if you're completely baffled by this question, is to go, oh, let me just do 1, which is the mass, over the AR, which is 40. And guess what? You will have picked up one of these two marks. And so even if you can't get past this point, you are on a level 7 for this question because you've got 50%. So that's why I'm saying, peeps. Right, that is the number of moles. That was the MR or AR in this case because it's just a single atom. So 0.025 moles. Now, this tells us that Avogadro's constant is 6.2 times 10 to the 23 per mole. What do you think we have to do? That is the number of argon atoms in 1 mole. That's the number of pencils in a mole of pencils. That's the number of arm hairs in a mole of arm hairs. So if that's the number of argon atoms in a mole of argon, how much is in 0.025 moles of argon? Well, if we have 1 mole of argon, you do 1 times 6.02 times 10 to the 23, and you get that answer. If you had 2 moles of argon, you do 2 times 6.02 times 10 to the 23, because you'd have 2 lots. So you'd have double the amount of particles. Here, we don't have a lot. So we're going to do this number times 6.02 times 10 to the 23. And that is going to give us our answer, which is 1.505 times 10 to the 22. So 1.505 times 10 to the 22. And that's going to get you the second mark, peeps. Okay, so first mark, second mark. Like I said, once you see numbers, circle them and identify the chemistry equation you need to use. All right, let's move on. This question is about electrolysis. Some metals are extracted from molten compounds using electrolysis. Why is electrolysis used to extract some metals? It's because those metals are too reactive. The metals are more reactive than carbon, so they can't be extracted by. They cannot be extracted by displacement. Whoopsie. with carbon. Basically, we can't use the normal methods of extracting. Like if we had copper, carbon is higher in the reactivity series, we could just get copper to react with a copper compound, and the carbon will push the copper out. And carbon's relatively cheap, right? It's just like coal. So it's quite cheap. Whereas if you start to use more expensive metals to displace things, well, they tend to be quite expensive. So not a good idea. Use electrolysis. Aluminium is produced by electrolysis of a molten mixture. What two substances does it contain? So aluminium in its raw form is called aluminium oxide. It actually comes from a rock called bauxite. But at GCSE, we just need to say, yeah, it contains aluminium oxide, which is the main component of bauxite. That's the formula Al2O3, or you could just write aluminium oxide. Now, there is another substance that when we melt the aluminium oxide, because we want to make it a liquid so the ions can move and we can do electrolysis. Otherwise, if it's solid, the ions can't move and charge won't go through and you can't do electrolysis. But the other thing we want to add is something called cryolite. And if you don't remember cryolite, you should cry a lot. But you don't need to cry a lot because you remembered it. Cryolite's a catalyst that lowers the melting point, makes it easier for us to melt the aluminium oxide. We use less energy. It's better for the environment because using less energy means less electricity or whatever, less heat, which means less carbon dioxide, less greenhouse gases, all of that business, and saving dollars, right? So yeah, it knocks like 1,000 degrees or more off of the melting point of aluminium oxide. Cool. Let's move on. And remember, you better remember cryolite, or you'll be crying in the exam. Right, copper and chlorine are produced when molten copper chloride is electrolyzed. Complete the half equation at each electrode. Half equation at the negative electrode. So negative electrode is where positive things like metals go. Metals always go to the negative electrode. And something always happens at the negative electrode. Because it's negative, it contains loads of electrons. So these bad boys are going to pick up some electrons. How many, you say? Well, that's 2 plus. So it's going to pick up 2 electrons. And it's going to become Cu, but no charge. So what's happened is the 2 plus has joined with 2 electrons and equals nothing. Been cancelled out. 2 plus and 2 minus is 0. So we don't write anything. That is just a normal copper atom. And this, by the way, if you wanted to know, is called reduction. And a good thing to note for electrolysis is that reduction always happens at the negative electrode. You gain electrons. Remember oil rig? So you have rig, reduction is gain. Guess what? Down here, we're going to do oxidation. If at one electrode you have reduction, at the other you must have oxidation. So half equation at the positive electrode. At the positive electrode, we're going to lose electrons because they're going to leave and jump into that positive electrode. So we've got 2 chloride ions. Guess what? That's a big times 2. So that means there are 2 chlorines there. So we're going to form a chlorine molecule. So we've essentially gone from 2 chlorine ions like that, each one with a minus, because that's what the big 2 means. And then on the other side, they have joined together like this. They're sharing. So we draw them as Cl2 like that. Now, what happened to the 2 minuses? Well, because they're now sharing, they don't need these electrons, these minuses. So they're going to give them away. And this is the bit that screws with people's minds, and they find it really hard to get over is, but sir, why do I put a plus? That looks like it's getting electrons. It's plussing electrons. And that's the hardest thing in electrolysis that mashes everyone up. You just wish you could say chlorine, take away 2 electrons, but you can't. You've got to think of the plus as meaning and when it's on the right-hand side. So chlorine and 2 electrons, it's given away. Okay? Bit difficult. But there we go. It's an equation. It's math. So it's like saying like you've shifted it. Anywho. Right, that is oxidation because the chlorine has lost these 2 electrons. So oxidation is loss. The other thing to note, if you're doing 2 half equations for the same electrolysis cell, electrons will appear on the left-hand side at the negative electrode and on the right-hand side at the positive electrode. So electrons are always on the right at the positive and always on the left with the negative. So yeah, anywho. Probably one of the hardest things in GCSE, this, and it comes up every single year. Hasn't been a year where electrolysis hasn't come up, but it's not normally that many marks for the half equations. You can get the other marks just by memory recall, even if you find this bit a little bit challenging. Calculi. Figure 4 shows the apparatus a student used to electrolyze copper chloride solution. So we've got the power supply, we've got copper chloride solution, and we've got pure copper electrode. The student measured the mass of copper deposited on the negative electrode after 60 minutes, compared the mass deposited with the expected value. Suggest two reasons why the mass deposited was different from the expected value. So the student measured the mass of copper on the negative electrode so copper's coming out and is joining here, and this is getting heavier and heavier. And it's saying, however, when they measured it, the mass was different than the expected value. Now, because they've said the mass is different, you're going to get a mark for saying whether it's heavier or lighter, and then saying why. Now, I think this is quite a hard question. I think it's quite hard. So why would the mass be different? It means there's some sort of screw up going on here. So maybe the copper chloride solution, is stronger or weaker. Copper chloride concentration is different than known. So it's not the same as what they think. The copper chloride solution isn't what they think. Maybe some copper metal fell to the bottom. It sounds silly, but they're expecting all of their copper metal, as the copper ions come out of here and become copper atoms, they're expecting all the copper metal to go on there. So it's getting heavier and heavier when they weigh it. But what if some of the copper, once it has become copper atoms, doesn't, it falls or flakes off? There we go. And also when they take it out, it's going to have, when they take this electrode out, another thing we can say, when they pull that electrode out of the solution, all right, it's going to have some copper on it. And let's say we want to weigh this, right? So we're like, right, I want to weigh it and find out how much it's got bigger. That way I can work out how much copper is on there. Well, what if they don't dry it properly and it still has some water on it? Then you're weighing the water as well. So you're going to get a different value than you expected. Obviously, it's going to be heavier. So we might say some solution, it might not be water, it's copper chloride. So some solution is on the electrode. It hasn't been dried properly or whatever. You should dry it with a paper towel. Again, when you dry it, you might flake copper off, so some copper might fall off when drying. There's all sorts of reasons why it might end up less than expected, but I think that's a difficult question. Okay, 5.5, we've got a graph. Oh my God! Figure 5 shows the expected mass of copper produced every minute. Determine the expected mass of copper after 24 hours. So you might say, but this doesn't go up to 24 hours, but it's a straight line. So it's telling us that we should be able to make a prediction, right? So let's work it out how much copper was made after 30 minutes and then times that up to an hour and then by 24 to 24 hours. So how much copper was made after 30 minutes? So I'm coming up to 30 and I'm going to, why 30? I could do 10. We could do 10, but I'm going to do 30, a little bit more accurate to use a bigger number, right? So, oh my days. It looks to me like after 30 minutes, it's there. Now, I need to work out what each one of these squares is worth. So that's so it's only 1 and there are 5 squares. So 1 divided by 5. Each square is worth 0.2. So each square is worth 0.2. So that is 5.2, 5.4. And that is after 30 minutes. So I reckon the examiner sees this on your paper, you're getting one of those marks, regardless of whether you screw the rest of it up. So always show your working out with lines and your ruler on the graph to show your readings, note them down. So 5.4 after 30 mins. So what's it going to be after 24 hours? Well, let's first of all say, let's times it by 2. Times 2 equals 10.8 after 1 hour. So what's it going to be after 24 hours? Let's times it by 24. So 10.8 times 24. And that equals 259.2 equals 259.2. And that is grams. No, it's not. It's mg, milligrams. Determine the expected mass of copper after 24 hours. Okay, so hopefully that makes sense. You're going to pick up marks for like working on the graph, reading off the mass of copper after 30 minutes. You didn't have to do 30 minutes. We could have tried it at 10 minutes, see if we get the same answer. So like with 10 minutes, it's 1.8. So let's try 10 minutes and 1.8, see if we get the same answer. So after 10 minutes, it was 1.8. So let's do 1.8 times 6, because there's 6 lots of 10 minutes in an hour. And that gives me 10.8. And then times 24, that gives me 259.2. There you go. Doesn't matter where on the graph we draw that line going across. It was just easier for me to times 30 minutes up into 24 hours, but you might find it easier to do 10 minutes or 20 minutes. It's a straight line, so the gradient's the same everywhere. Brilliant. That's going to give us 3 awesome marks. Let's move on. Let's not stick random ticks on a page. Silver nitrate solution is electrolyzed. Figure 6 shows the change of the mass of electrode over 10 hours. Here's the mass of electrode in grams. Started off as whatever that is, ended up over there. Determine the mass of the negative electrode at the start. Oh, nice and easy, right? We just need to work out what each square is worth. So what I do here is I go, right, there are 10 squares, but the value is 0 to 5. So I start with my value and then divide it by the number of squares. So if you want to know that, if you're ever working out the graph on the y-axis, this will often be difficult. You want to do the value divided by number of squares, and that gives you the value of each little baby square. So the value of each of these squares is 0.5. No, it's not. Yes, it is. So 0.5. So when I come up here, that's 5. If we go down to 0.5 from that, it can't be yeah, 0.5. So 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. Now here's the difficulty. It looks to me, I'm not sure they'll accept 4.5 here. It looks to me like it's bang smack in the middle of a square there. So it's between, and I think they'll give you the range here. It's between 4.5 and 5.0. I'm going to split the difference and do 5.0 take away 4.5 equals 0.5, then divide that by 2. So it's 0.25 plus 4.5. Yeah, so because my maths is so bad, I make that out to be 4.75, okay? But I think there will be a range in the exam. They normally give you a slight range. So if you read that as 4.5, I think they'll allow you. But I'm giving it 4.75. I think it's just in between. Lovely bubbly. So let's move on. It's quite hard, that question. Calculate the gradient of the line in figure 6 and give the unit. I'm going to show you how to do that. So the gradient is nice and easy. It's a straight line. So all we got to do here is, what did it start at? What did it end at? We've got to do change. Gradient is equal to change in y divided by change in x. This is the y-axis and this is the x-axis. So by how much did the y change? How much did the x change? Divide them. And the units, you just take the unit from the y and the unit from the x. And so you're just going to go G line hours, right? G line hours. That is the unit, like that, grams per hour. And that's how you work it out. Okay, so let's get on with this and stop whiffling. Well, X is dead easy, isn't it? Because look at the change is 10. So I know I've got 10 at the bottom. That's my x-axis is 10. But my y-axis is a little bit more difficult. I made that as 4.75, but that looks like it's done the same thing. So what a pain in the ass, right? 5.5, 6, 6.5, a 6.75. So we've gone from 6.75 from 4.75. So I make the gradient 2 divided by 10. So if we do 2 divided by 10, we're going to get 0.2. And that is my gradient. And I think we're going to pick up 3 fat marks for that. And once again, there's always a slight variation with graph reading. So they might have a little range because of eyesight and stuff like that. Okay. And the units, by the way, 0.2, and just to go over the units again, it's grams per hour, and you're just reading that off the graph. Grams divided by hours is what we did. So it's G per H. All right. Enough of that. That's the end of that question. We're on to the last question. Woohoo! This question is about sodium. Sodium reacts with chlorine. What is the balance equation for the reaction? Well, sodium is in group one, G1. So it's gonna want to be, it's gonna end up being +1, and chlorine is in group seven, and that means chlorine is going to be -1, and they're going to get together in the formation of NaCl, right? So anything that ends NaCl, we're good. That's NaCl2. Nah, can't be NaCl2 because look, two minuses and a plus, that doesn't work. So it can't be that one. And it can't be Na2Cl because if I had two NAs like that and a Cl minus, they don't cancel out. They don't balance evenly, the electric charges. So we bash out that one. That one's wrong as well. Um, and now we know it has to be one of these two. But check out chlorine here. Chlorine is a single atom there. What you should know about group seven are diatomic molecules. So they have to have Cl with a 2 after it. That's why we end up needing two sodiums and that and that. You can learn that one off by heart if you like, but there we go. Okay. Lesson C. Oh my days. 6.2, hot sodium is put in a glass jar. Um, Describe the observations made before, during, and after the reaction, 3 marks. So if you put sodium in a glass jar of chlorine, what color is sodium? Sodium's silver. I guess it's hot. But yeah, chlorine's a green gas. So we're going to say pale green gas. That's my observation. Bash, 1 mark. Thank you very much, Bob. Sodium's a silver metal. You might want to say that. During the reaction, chlorine and sodium react quite violently. It's very exothermic. You're going to get a lot of heat. So I'm going to say bright flame. So you're going to see a flame. We're going to get a flame, lots of light, bright light, covering all my bases there. Sodium generally burns with a yellow flame, but there we go. You're going to get a bright flame. And then after the reaction, you're going to be left with sodium chloride. You put it on your chips. What does it look like? You're going to have a white solid. You might say, sir, have I really got to remember that? Listen, every compound in chemistry that's solid is white unless you're a transition metal. Okay, let's move on. So sodium chloride is going to be white. Magnesium chloride, white. Sodium oxide, white. Aluminium oxide, white. Calcium oxide, white. Calcium hydroxide, white. Lithium chloride, white. Lithium fluoride, white. You get the idea, right? Any group one, two, or three metal joint with something else, it's going to be white. When it's solid, it's going to be colorless when it's in solution. I'm nearly done. I'm nearly done. I don't think I will have any more coffee. My head might explode. Explain why sodium is less reactive than potassium. Okay, so if we check them out, here is lithium. Didn't ask us about lithium. What am I doing? Okay, so lithium is in period two, as two shells. Oh my days. Don't go down this path, Tom. Sodium is in period three, has 3 shells. I'm going to be really long. Potassium is in period four. Guess what? Potassium's got 4 bad boy shells. Okay, let's check it out, check it out, check it out. Why is sodium? We're really looking at this one, folks. We're not interested in lithium. I just drew it for the sake of it, because it's part of the group. And this pattern carries on down group one, group two, and group three. It's the same pattern in all of them. So as we go down the group, what is happening? There are more shells. So I can either argue this as to why potassium is more reactive. I'm going to go down that way. Or I could say why sodium is less reactive. I'll give you both answers. They're both worth the same. But I'm going to go with potassium first. So potassium is more reactive. Um, as it has more shells. Guess what? You could say instead, it is a bigger atom. Either one is good, so that is going to get you a mark. Bosh! Then what we want to say, it's bigger, it has, yeah, you get the idea. What I want to do is say, what do we call this electron? This is an outer electron. What are both of them trying to do? They're trying to give away an electron. They want to give away electrons. And what I want to say about potassium, potassium's electron is further from the nucleus. Boom! That's the second mark, peeps. So there we go. Its electron is further. Look, just to prove it. It doesn't actually prove it at all. Oh, look, there's the nucleus. There's the positive charge of the nucleus. That line is going to be bigger than this line. So it's further from the nucleus. Now comes an A-level bit I can add in if I want. But I could just say, yeah, I'll add that at the end, the A-level bit, because it all crosses over, and a lot of teachers have taught their GCSE students this, so it's always on the mark scheme in the except. But so we want to say it has more shells, bigger atom. Um, they want to give away electrons. The electron is further from the nucleus, so is less attracted to nucleus, um, or I could say less force of attraction to nucleus. Oh my gosh, I can't spell. And you might say to me, sir, haven't you said it all? Isn't it? There's nothing else to say, and that's only 3 marks. Remember, I said they want to give away the electrons. So because it's less attracted to the nucleus, we would say it is easier to lose the electron. So what I can do here, guys, is also add in something called shielding. So potassium has more shielding. Now, I don't have to explain that. If you just put potassium has more shielding, you're going to get a mark. What does that mean? This outer electron is blocked from the positive charge by 1, 2, 3 shells in between, blocking that attraction. Imagine something's trying to pull you, but there are 4 barriers or 3 barriers in between. It's more than the 2 barriers that sodium has there, blocking that electron from the nucleus. So we call that shielding. There's extra shielding. The shells shield the outer electron from the nucleus. Now, what would I say if I wanted to argue this the other way around, which is kind of what the question asked, but you get all the marks for this version. Sodium is less reactive. So I'd say sodium is less reactive. It has less shells. It wants to give away electrons, and its electron is closer to the nucleus. So the electron's closer to the nucleus. So it is more attracted to the nucleus. There is a greater force of attraction. It's harder to lose its electron, and it has less shielding. So you just reverse. You'd say the same things, but reverse. Now you can see I've done 5 points there. Yeah, we like to do the extra. Okay. Oh my days, you're having a bubble, aren't you? It's the last question here. Geez, straight into a 6 marker. Okay, chlorine reacts with sodium and with hydrogen. Compare the structure and bonding in sodium chloride and hydrogen. Nothing to do with the reaction. It's just saying what's the structure and bonding in sodium chloride and hydrogen. So going to deal with it. Now, look, it says structure and bonding, and it wants us to compare. So I'm going to say what the structure is in each, and then what the bonding is in each, because that's what a comparison is. So I'm going to say sodium, it's easier for me to do the bonding first, so I'm going to do the bonding first. Right, sodium chloride has an ionic bond. Do I want to explain what an ionic bond is? Sorry, why not? An electrostatic force of attraction between oppositely charged ions, right? That is an ionic bond. So I would have my sodium plus whatever. I should really put the plus outside the brackets, right, mate? And then I'm not even going to draw the circle around it. This is just to show you. So this is the electrostatic force of attraction between sodium and chlorine. Whereas hydrogen has a covalent bond where a pair of electrons are shared. Let's just explain what a covalent bond is. Has a covalent bond, which is also the so they both have an electrostatic force of attraction. That's kind of a commonality, which is also an electrostatic force of attraction, but between shared pair of electrons and nuclei. Okay, and the nuclei. So what the hell do I mean there? Well, what I'm saying is, bish, bash, bosh. If you imagine you have hydrogen here and hydrogen there, they're sharing their electrons between the nuclei. So it's covalent. So I've compared the bonding. I can tick that off. Boom, done the bonding. One's covalent, shared pair of electrons, or force of attraction between shared electrons and nuclei. The other one's ionic. It's electrostatic force of attraction between a positive ion and a negative ion, or you can just say oppositely charged ions, as I did there. And now I need to talk about the structure. So, sodium chloride. And because sodium's a metal, if you can't work that out, you've got a periodic table given to you in your exam, and chlorine is a non-metal, so we know what they are. Sodium chloride has a giant, there's a mark, um, ionic structure. Okay, so giant ionic structure, that's going to get you a mark right off the bat there. So we've already secured at least 2 for that, maybe more for that, because we did that quite nicely. As a giant ionic structure, what we want to say is it is made of lots of strong ionic bonds, need lots of energy to break. It doesn't really ask us to compare their properties. So if I wanted to go into how it affects their properties, I'd say sodium chloride has a higher melting point. It's a solid at room temperature, whereas hydrogen's a gas. So I'd kind of explain that. So, but it doesn't really ask that. So maybe I shouldn't go into that. But what the hell? I mean, it'd be more streamlined if I didn't. I'd be sticking to the question. And this probably you shouldn't do. I'm going to put this in brackets. It's made of lots of stronger bonds, need lots of energy to break. So it has high melting point, is solid at room temperature. Okay, so that explains why it's like that. Now, I'm going to do the final 2 marks for explaining hydrogen. Hydrogen or hydrogen. No, hydrogen is a simple molecule, right? It's covalent. We already said that. You can call it simple covalent if you like. Small molecule, some examples allow, but best to call it simple molecule. Hydrogen is a simple molecule. It only has weak intermolecular forces between the molecules. Okay, so not a lot of energy needed to break. Now, this would explain if you had to, but again, I don't think you have to here, but this would explain. So it is a gas at room temp, has low melting point and boiling point. Yeah, it's already melted and already boiled at room temperature. So one of the things to note is that both contain a similarity, both contain very strong bonds. Like, it doesn't mean hydrogen has weak bonds. Look, this bond that's formed between hydrogen, those electrons, there's no shielding. They are close to the nucleus. That's a strong bond. Okay, you ain't breaking that bond. When hydrogens are solid, the particles are like this, just vibrating next to each other in regular pattern. But unfortunately, there is nothing in between here joining these 2 H's from adjacent ones together. So what happens is, my days. No, don't move that. Thanks, Bob. What? Jeez Louise. I had that right off my own back. When we want to boil hydrogen, all you're doing is breaking or overcoming the fact that there are no black lines in between the H's of different hydrogen molecules. So a hydrogen molecule has 2 H's, and what I'm doing is I'm pulling this apart to make it a gas, and that's easy because there's nothing holding it together. I'm not trying to break the 2 H's apart. That's very difficult. Okay, that is not easy. So don't say when you're dealing with things with a low melting or boiling point, don't say, oh, because the bonding is weak. The bonding is not weak. You're not breaking the bond. You're breaking intermolecular forces with these simple molecules. Okay, you're just overcoming these weird intermolecular forces. If I was trying to break sodium chloride, that is going to be an issue because remember, your sodium chloride looks like this. It is a giant ionic lattice, so it does have bonds in between the molecules. I know you said there's only forces. Well, this has actually got ionic bonds everywhere. There are no weak intermolecular forces in sight. There are black lines. We draw them with solid black lines in between each of the ions. So there aren't any molecules. There's no such thing as a sodium chloride molecule. We're not allowed to use the term molecule because they don't exist separately. Sodium chloride only exists in this giant structure where there are many, many strong ionic bonds. That is level 2 GCSER. I've outdone myself with that one. But you get the idea. That is a giant ionic structure. If you want to turn this into a gas or a liquid, you have to break every single one of these strong ionic bonds. When you want to turn hydrogen into a gas or a liquid, you do not break the bonds, the covalent bonds. You just separate them by breaking these weaky intermolecular forces. And here we go. That's 6 marks. Guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Oh, I better get off the coffee. before I
You're
get
still
arrested. Too much
here?
coffee makes me hyper.
It's over.